Hello, this is Mr. Manley. This is a video on systems of equations, and we're going to look at this from several angles. The first of which is what is actually going on here is that we have two equations, and if we think about these equations visually, I've got an equation which is going to be a line, and I've got another equation which is going to be a line, and the idea here is that we are trying to figure out where do these intersect. So when we say solve a system of equations, that means system, this word system means we have more than one equation, and solve means we're looking for that point of intersection. So whenever we see solve this system of equations, we're looking for the coordinates of a point, and that will be the place where the equations intersect. It'll also be points, the point that we find is also an xy value that will satisfy this equation. So when I find the x and y for this, and I plug in for x and I plug in for y, that means that this equation here, the result will equal 1 for that x and y that I find. So that's what we're doing. We're going to look at this in a few different ways. The first is called linear combination. And in a linear combination, that basically means, or it does mean, that I am combining the equations by addition or subtraction in order to eliminate one of the variables. So when I look at these two equations and say I look at the x, I want to take the x value and make the coefficient similar or the same so that I can eliminate that value or that variable. So in this case, if I take the first equation and multiply that equation by 5, and if I take the second equation and multiply that equation by 9, I'm going to have the coefficient on the x values are going to be, they're actually going to be the same and opposite. So the first equation and the second equation, and now you can see that I've got those coefficients matching up. They're opposite in this case, so I'm going to add these two equations together. And that'll be negative 45 plus 45 will be 0. And I'll do 35 plus 27, which will be 62y. And I will do 115 plus 9, which will be 124. And then solving for y, I can divide both sides by the 62. And of course, 124 divided by 62 is equal to 2. And I have found that y is equal to 2. That is the y coordinate of my solution. Let's place that in the position here. Y equals 2. And now we're going to find x because we know y. And I can find x by substituting this 2 into that equation or into that equation. It does not matter which equation I substitute. I'm going to choose the second equation. That would be 5x plus 3 times 2 equal to 1, and then solving for x, 5x is equal to negative 5, and x is equal to negative 1. And of course, that x coordinate is going there, and that is my solution. That is the point where the two equations intersect. Okay, now we're going to take a look at solving a system of equations using substitution. So in the first one, we had this system of equations, and we solved it by this method called linear combination. Now let's take this system and say we're going to solve by substitution, which actually I'm not going to do because it would be an inefficient way to do this one. But if I were going to do it, I would take this equation. I could take either equation and solve for either variable. So let's take this equation and let's say that I solve for y. So I'm going to say 3y is equal to 1 minus 5x, and then I'm going to divide by 3, and I'll have 1/3 minus 5/3 x. And then what I would do is I would take that, I would say, since y is equal to this, I can substitute for y in the other equation. And then I would have an equation in a single variable. Can you see that? That if I substituted for y, if I put this value, if I put this expression in for y, then I would have that first equation would have only x, the variable x, and I could solve for x. But you can see that would not really be a very effective way to do that. Now, if I had an equation like this, it would be convenient to do this by substitution. If I take this first equation here, and let's say that I solve for y. So I'm going to say that y is equal to 2x plus 8. So do you see that? How I took this equation and I solved for y. Y is equal to 2x plus 8. Now I'll take this 2x plus 8 here and I'll substitute it for y in this other equation. So I'm going to substitute now. Substitute, and I will have 3x plus 4 times 2x plus 8 equals 10. So do you see that? This equation, I brought down the 3x, and then I brought down the 4, and then instead of bringing down the y, I did this substitution of what y is. Okay? So take a moment and make sure that you follow that. And then from there, I can solve for x. So I've got 3x plus 8x plus 32 equals 10. 11x is equal to negative 22. When I do 10 minus 32, x is equal to negative 2. And then from there, again, recall that when we say solve this, we're looking for the point where the two equations intersect. And as of right now, I have found the x coordinate of that point. Now, I trust that you know how to find the y coordinate at this point, so I'm not going to continue on and do that. But from here, we could find the y coordinate. Okay, let's look at one more thing. Let's try going back to this equation, which we already solved by linear combination, and we decided that it was inefficient to solve it by substitution. Well, let's look at something else with this. How about we look at it graphically? And really, graphically is not a way that I would probably ever go about solving a system of equations, but from a conceptual standpoint, we definitely want to understand things visually. So I am going to look at that, and you may be held accountable for that. So what I'm going to do is I'm going to number both of these equations. I'm going to call this equation number 1, and this is equation number 2. And then I'm going to go in to each equation, and I'm going to find the x and y intercept. And let's see how that works out for us, because the x and y intercept is kind of convenient to find. Not always the most convenient, but let's go ahead and take a look at that. So this is x, and this is y. I've got a problem with my. There we go. Y. Okay. So let's see. If x is 0, I'm going to use a different color here. If x is 0, then y is 23 over 7, which is, what is that? 3 and 2/7. If y is equal to 0, in this first equation I'm talking about, if y is equal to 0, then x is equal to negative 23 over 9, which is, what is that? That is 2 4/3, negative 2 4/3. So that's for the first one. And then for the second one, if x is 0, then y is equal to 1/3. And if y is 0, then x is equal to 1/5. So I'm not writing all of that out. I'm able to just look and say, well, if x is 0, then that means that's going to zero out, and then I can see that y would have to be 1/3. And then I think to myself, if y is 0, then that's going to be zeroed out, so x would have to be 1/5. So hopefully you don't need to see that all written out. Okay, so now I've got the x and y intercepts for both number 1 and number 2. Let's take number 1 first. So number 1, and let me take a look. I think my scale is going to be something like, I think I'll make my scale something like 1, 2, 3, like that. That might be a convenient way to do it. 1, 2, 3. Okay? All right, so the first point that I'm going to look at here, this point here, I'm going to look at x is 0 and y is 3 and 2/7. So let's go 0 and then 3 and 2/7. So that would be, there'd be 1, 2, 3, and then a half would be there. So, and I'm not quite up to a half with 2/7, right? So it's going to be in between there. And then the other one is this negative 23/9. So negative 23/9 is equal to 2, that's 18, and then 5/9, negative 2 and 5/9. So I'm negative 2 and 5/9 on the x-axis, and it'll be 0 on the y-axis. So let's go over here, negative 1, negative 2, and then 5/9 is a little bit more than a half, right? So it's going to be like there. All right, and that's my first one, like that, and I'm going to number it, number 1, just to keep track of things. And then my second one here is going to be 0, 1/3. So that's 0 on the x-axis, and then 1/3 right there, or around there on the y-axis, and then 1/5 0 on the x-axis. So this is not great, my scale, right? It's not great for the scale that I chose here, but we're going to go with it. Too late now. All right, so I'm going to go through those 2 points. You understand that those 2 points are so close together, I question the accuracy of this line, but it should at least give us a general idea. And then I'm going to go 2. So look, if we did that graphically, if we did it graphically, then we would be saying that that's our solution. And where is that at? That's at negative 1, 2 is what it would look like graphically. Well, let's look at what it actually was. Well, how about that? For all of my scaling issues, the answer is actually negative 1, 2. So that did work out, luckily, graphically. But I didn't really need it to. I just wanted to use it to illustrate what this all means graphically, because we've really been working algebraically, and I wanted to look at it graphically as well. And like I said, this would not be a method of choice, but in order to understand what's going on with these and to actually see it, I think is valuable. All right, so those are that's some discussion of systems of equations. looking at it in a few different ways and trying to understand the conceptual foundation of this topic. And I hope that helps. And as always, if you have any questions, get those to me.